Good morning and welcome to Advent of Code in F#, day 10. We're already 10 days in, so I figured let's pull up my Christmas sweater. I don't know if you'll be able to see it, but it's a Star Wars themed Christmas sweater. And I'm a bit proud of it, so yeah, there we go. Let's dive right into today's puzzle. Adapter array. Patched into the aircraft's data port, you discover weather forecasts of a massive tropical storm. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off! Exclamation mark. Okay, dead batteries. I'll need to plug it in. The charging outlet near your seat produces the wrong number of jolts. Not volts, but jolts. Okay. Always prepared, we make a list of all the joltage adapters in our bags. Cool. Okay, so we have a bag full of joltage adapters. It's rated for specific output joltage, yeah. So our input is a specific output joltage. Any given adapter can take an input 1, 2, or 3 jolts lower than its rating. Okay, so we have an output joltage and any adapter can take an input 1, 2, or 3 lower. And still produce its rated output joltage. Yep. In addition, our device has a built-in joltage adapter rated for 3 jolts higher. Okay, so we're working with adapters in our bags, and the device has a joltage adapter for 3 jolts higher. Okay. So if you have adapters for 3, 9, and 6, the device's built-in adapter is 3 higher than whatever we got. Okay. Charging outlet near our seat has joltage rating of 0. Joltage ratings, okay. And we're gonna test all our adapters, cool. If you use every adapter in your bag at once, what is the distribution of joltage differences between the charging outlet, the adapters, and your device? I'm gonna need an example for this one because it's practically Chinese. Suppose that in our bag we have adapters with the following joltage ratings. Okay, so that's the number of joltage ratings. With these adapters, your device built-in joltage adapter would be rated for... I'll look for the maximum value and add 3. That is... I can do that. Because the adapters can only connect to a source 1 to 3 jolts lower than its rating. In order to use every adapter, you'd need to choose them like this. Okay, so you have to make a chain of the adapters. And the input or the source has to be 1 to 3 lower than the rating of the adapter itself. Start with the outlet of 0 jolts, so then we need something between 1 and 3. Yeah, okay, that's clear. We have a 1, yeah. Then we can go to 4, yeah, then 6, or 5, or 7. And we take the lowest number, yeah, okay. We just chain them from lowest to highest. 6 and 7, yeah. And then 7, we need 8, 9, or 10, but we only have 10, sure. Okay. Okay, so everything's clear. And then at the end, our device's built-in adapter is always 3 higher than the highest adapter. In our case, the highest adapter is 19, so it's always 22. Okay, so that's, I think, the easy part. Just if we sort our input from lowest to highest, don't we like get the correct order? I think so. If you look at the example, that's lowest to highest, right? Yeah, that's lowest to highest. Okay, and then we have differences of joltage. 7 differences of 1 jolt and 5 differences of 3 jolts. Okay, so that's all just stating some random facts. Here's a larger example. There are 22 differences of 1 jolt and 10 differences of 3 jolts. Okay, so the jumps or the differences in jolts appear to be somewhat important. Find a chain that uses all of our adapters to connect the charging outlet to our device's built-in adapter, and count the joltage differences between the charging outlet, the adapters, and your device. And then we look at the number of 1 jolt jumps and the number of 3 jolt jumps. Okay, I think for part 1 we can take a shortcut and just sort our input list. Let's try that. No, let's not update our Visual Studio just yet. So we have 101 input joltages, and we can rate them. Oh, I have something from yesterday in my REPL. Let's clear everything. There we go. Morning coffee. Will the REPL please wake up? The REPL has awoken. Yeah. How big are the numbers? This looks like in integer range. Yeah, sure. So let's parse them into integers. Shall we go with the naive strategy of just ordering or sorting from smallest to largest? Why the heck not? I hope this is just a sort. Yeah, this is just a sort. Okay, and then we need the differences. We start at 0 and we end at +3. I'm just gonna append the 0 up front and the +3 at the end. Yeah, let's do that. So the total chain is, let's make a list of what we just had, so we can easily append, and we append 0 to sort it, and we paste the last element +3 at the end. So let last is sorted last, and so that's last +3. I'm wondering if my resharper tools are working. No, they are not. Okay, so this is the total chain of joltages with the outlet at the start and our device adapter, which is a +3. Let's calculate the, what was it? What do they call it in the exercise? Differences of joltage differences, let's call them that. We were looking at pairwise yesterday. Let's use pairwise. So pairwise, what does it do? Let's generate a quick example. If I take a list of 1 to 5 and I want it pairwise, it'll generate pairs between every element in the list. So 1, 2, 2, 3, blah, blah, blah. And I think that's exactly what we can use in our chain. So if we pair them up, now we have all the pairs, and let's calculate all the differences. Just mapping a function that takes pairs, and let's calculate the delta. There we go, -1, -1. Okay, I want to see if we have 1s and 3s, so there are no 2s, only 1s and 3s. And now we count them. So let's split them up. Now we have the 2 partitions. Let's count them. Let deltas is, and 1s is the deltas. Sorry. the first set of deltas is the ones, and we need the list of ones so we can count it. Is there a shortcut here? I don't care. So these are all the ones we have. Let's count them. I'm gonna use lists because it's not that big of a data structure and we do need to loop over everything. So let's just use the list functions and then we can access it like this. Yes. And the threes are the second group, and we need a list of threes. Yep. Let's run that part. Cool. Let's multiply ones and threes. Cool. We have a number, and if the assumption of sorting is correct, then it should be a valid number. Cool. Let's go to part 2. And now I'm guessing our sort the input strategy will fail. First drink. To completely determine whether you have enough adapters, you'll need to figure out how many different ways they can be arranged. There we go. Every arrangement needs to connect the charging outlet to your device. The previous rules about when adapters can successfully connect still apply. First example above supports the following arrangements. So this is sorting. First line is our strategy, sorting everything. What's different on the second line? There is no difference. We're just taking bigger jumps, so we're not taking every adapter in our bag in the chain. Cool. I'm looking for... It's always increasing, right? The numbers always go up. Just take jumps. Okay, I mean, oh, we just need... I thought we might have to find the shortest chain, but it looks like we need to count all the number of possible chains, the total number of arrangements. We have a second example with a lot of arrangements. In total, this set of adapters can connect a charging outlet to your device. In 19,000 distinct arrangements. Let's not do this by hand. We glance back down at our bag and try to remember why you brought so many adapters. Exactly. There must be more. Oh, this is interesting. There must be more than 1 trillion valid ways to arrange them. So I'm guessing that brute forcing our way out of this puzzle will not really work, or it'll take more than 3 seconds to compute. Interesting. Interesting. Record scratch, hold up a minute. This is a yo from the future talking. The next 1.5 hours of the stream were me completely fiddling it and messing around with stuff that didn't work out. So I decided to actually cut the stream and give you a recap of the situation here. So, spoiler, I solved part 2 and I had a lot of problems with it. And I'm not gonna just show you my solution. I'm gonna show you like my thinking process, but in a sped up manner. So it's going to be fast forward through my last 2 hours. And I hope it will take less than 2 hours to explain my thinking process, but I'm thinking it well. So we just read part 2. Let's show my screen. There we go. We just read part 2 and we're trying to find the number of distinct ways in which we can arrange the adapters to connect the outlet to our device. Quick spoiler, it's a really big number. So I decided to parse my input as longs or int64s because I had some issues with integer overflows. So that's one part of the spoilers already. Now, what I want to do for the remainder of the video is take you through my thought process. So not the 2-hour struggle. I'm going to spare you those details, but I will take you to every step of my thinking process. And as I mentioned a couple of minutes ago, I first try to brute force my way out of here. So let's do that as well. So let's take the small example and let's try to brute force it. There we go. Let's put it in an array or a list. There we go. Yeah, sure. Let's replace the new lines with separators. There we go. Maybe I should have added long so that all the integers are longs. And let's try that again. There we go. So yeah, this is the example. Almost the example, sorry. This is the example. And let's try to write a brute forcer for this. So let's write a solve function for some given input. And it returns the number of possible arrangements of the adapters. Let's not call it input, but adapters. There we go. I'm looking at the time. Do I have a time? Yeah, I have a time. Just making sure that I'm faster this time. So, first thing I do is same thing as part one. It's sorting it. So, example, let's sort it. Let's run example. So then we have the sorted array, and the sorted array will be something like this. Yeah, 1, 4, 5, 6 up till 19. This is not example. This is adapters. And when we have sorted our input, let's append the device, the internal adapter of the device, to the end. So let all adapters is sorted plus a single element, namely sorted the biggest number, which is the last number if it's sorted, plus 3. So this is all the adapters, and if we now write a function to calculate the number of paths, calculate a number of paths starting at the voltage 0 for the outlet and give it all the adapters. Let's put some parentheses here so the compiler is happy. And if we write a recursive function that can calculate the paths given a voltage and adapters, and let's make it recursive, then we are all set. So for the example, solve example should be 8, if I remember correctly. Part 2, diggity. Yeah, so for part 1, we're expecting 8. So let's write a test to see when we're done. We should get 8 out of there. Example, why are you int list? Yeah, we're working with longs, not with integers. So let's make everything a long, every of my constants. Then type inference nodes. Okay. Everything is a long. Cool. And let's also make the return type a long. And if we make the return type a long, our test should also expect a long. I do hope int64 is long, otherwise I'm making a fool out of myself. But here we go. So we are at this recursive function part. I was thinking, I drew the example. So yes, you can see it here, the example. If you sort the list, it's like 1, 4, 5 up until 19, and there's a 22 at the end, but it doesn't really matter for the search space. This is the brute force algorithm. So start at 0 and then take the first element, or maybe I'm gonna draw the 0. So start at 0, there we go. and then look at what other adapters can we reach. So which adapter is between 1 and 3 higher than 0? There's only one, which is 1. The next one is 4, and then it gets interesting. After 4 we can pick 3 adapters that will connect, so 5, 6, or 7. If we take 1, we can continue our search space all the way up until 22 or until 19. And you'll see a lot of duplication here, so brute forcing, or a naive brute force way, will do a lot of duplicate work, but that's not the end of the world for a small example like this, because if you see, it fits on one drawing board, so let's brute force it. So strategy is, when you're at a certain joltage and you have a list of adapters, look for all the possible adapters. So let's take, for example, 4 as the current joltage we're at. And then we know that 5, 6, or 7 are like valid candidates to continue our chain. And that's all we need, basically. So, yeah, so let's do that. Let's first calculate the candidates. So if we're at the current joltage, for example, 4 in our drawing, then we need to look at the adapters in here that are valid candidates for continuing the chain. So let's write a function, candidates, which take a joltage as well and a list of adapters. And let's just we need every adapter that's within range of the current joltage, and range is 1, 2, or 3 difference. Yeah. I'm only thinking. Yeah, let's also make this a recursive thing that'll make it a bit easier on my brain. So if adapters is empty, we have no more adapters. Yeah, then we have no more candidates. Sorry. If we do have adapters, an adapter and the rest of the adapters, if A is in range of joltage, so if the difference between A and joltage is smaller than or equal than 3, so joltage is 4 and these are like bigger numbers, yeah, then return A is a valid candidate. Oh, and by the way, let's also keep track of whatever comes after A. And we do the recursive call, so we calculate the remaining candidates, if there are any, for the same joltage in the rest of the list. So this part of the code makes an assumption, namely that adapters always contains adapters that have a higher joltage or an equal joltage to the joltage we get in. But yeah, that'll work out. And otherwise, so empty list, do nothing. If we have one in range, cool. If we have none in range, or like it's a non-empty list, but yeah, this threshold is like we overshot the threshold, then also we have no candidates. So there we go. Let's test this quickly. Let's test candidates with let's go with the example. So 4 and all the rest is 5, 6, 7, 10, whatever. So if we have 4 and we have a list of 5, 6, 7, 10, and whatever, what does this give us? It gives us 5 as a candidate and the remainder, 6 is a candidate and the remainder, and 7 is a candidate and that's the remainder. So that looks good. That is exactly what we want for a brute force. So I'm gonna encode this in a test. There we go, and the expected output looks correct, so let's copy paste it. Yeah, so that's we have solidified this fact. No, we haven't. Oh yeah, the 8 is a problem. This one is correct. Cool. So now we can generate candidates. We can make this function tail recursive quickly because it's not tail recursive now, which means after the recursive call, we still have to do something with the result from the recursive call. And for things like maybe this, where you're generating trillions of combinations or worse, let's quickly refactor this to a tail recursion. The way I typically do it is just nest the current function into an outer function like this. That one does not have to be recursive. For clarity purposes, I'll call the inner function candidates prime. And let's just call candidates prime with the input parameters. So nothing changed except that I wrapped the function in another function. That's not very interesting. It gets interesting when I provide something called an accumulator, or yeah, it's a list that contains the result basically. And if I provide the accumulator here, then we can start keeping track of the result in that accumulator variable. So what does it mean? If we have an empty list, then whatever we calculated up until now is what we need. So we just return the accumulator, same for this case. But in the case where we actually found a adapter within range, this is basically a valid candidate. Instead of appending this to the recursive call, let's do something else. Let's take the accumulator here, but let's cons the value we just calculated. So this is functionally identical as the non-tail recursive variant, but now the outer statement is the function call itself to the function, the recursive function. So now we have tail recursion, which in general is a bit more fun. If it worked, it's not working. What's wrong? 5, 6, 7, yeah. Oh, it's giving me 7, 6, 5. It's reversed the order. Don't think that's really a problem. I don't think that's really a problem actually. But for brevity's sake, let's just reverse the result we get from that recursive function. And that should remain the same. Yes, we still have a candidate generator. So now we have a function that generates like all the next potential adapters we could take to build a chain. So how do we proceed from here? Let's match on adapters. And if we have only one element in the list of adapters, yeah, that's easy. We only have one possible path. Is that true actually? Yeah. So let's assume that there's always a valid solution that then this works. Otherwise, non-empty list. Yeah, non-empty list. What do we do then? Let's generate the candidates for the current joltage in our list of adapters. So these are all the potential candidates and the remainder of the adapter string or list. So it's a sequence of in64s and a list of in64 pairs. So yeah, that's correct. And then we need to do something for every of those generated candidates. We don't actually, yeah, sure, let's keep going. So for every candidate, we have to recursively calculate the number of paths. So for every candidate, let's do a map. Calculate the number of paths for this candidate, and candidate itself is a pair of an adapter and the rest of the adapters. So for every candidate, we calculate the number of paths starting from that adapter and all the rest. And that means we have our number of paths for every candidate. And if we just sum all the possible paths for every candidate, we have the current adapter's number of paths. So if we just do a sum, there we go. And it's silly now I see this temporary variable. So there we go. And let's not return 1, but 1 long. No, that's not why this is squiggling. Where do we have an hard-coded int? There we have. Everything is a long. So there we go. Everything is a long, so also my example should be a long. Yes, that's true. Silly mistake. Go, go, go. Now we have time. I spent like 2 hours on this puzzle already, so what's another 5 minutes, right? There we go. Candidates still works, yes. Solving still works. So if we were to just brute force our way out of this, we would be done right now, because this is working. But if you try to run this on the input, you'll quickly see that your CPU will start to smoke and catch fire because there's a trillion combinations and this approach does not really scale. So we need a smarter approach. And in functional programming, whenever you hit things are blowing up, you have a couple of tools you can grab for. But in order to pick our tool, let's look at the search space first. Now let me grab my drawing apparatus. There we go. So this is the search space, and you'll notice that, for example, if you look at the long string in the end, 11, 12, this part, that's duplicated a lot of times. So that's here, 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 and a subpart of that was the 12 thing. That's here, 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 and it gets even better, like the 10 thing here, and then the whole sequence here, and the whole sequence. That same split is also everywhere. So we're doing a lot of duplicate calculations here. And when you're programming with recursion and you see like this duplicate search space navigation, there's a word that comes to mind and it's called memoization. But it's a fancy term for just keeping intermediate calculation results into a dictionary or a map, and before you calculate something, check whether you've calculated the value for that particular input, check it in the dictionary, and if it's already calculated, just read out that value, don't try to calculate it again. So that's memoization, and that's something we are going to implement right now for our brute force algorithm to make it significantly faster, actually. And this is where I hit a brick wall again, because I like to write F# with immutable data structures. So no mutable data structures, always defining a new value instead of updating existing data structures. But for the purposes of getting there, I had to take a step in between because my mind could not wrap around what was happening. And a step in between I would like to walk you through right now is just using a mutable C# dictionary as the memoization, or as the lookup table. So let's use a C# dictionary first. And it's not as pure, it's not as immutable, but it works a hell of a lot, or it's a lot easier to understand. So let's go. Where will we initialize our dictionary? This is the function. Yeah, let's initialize it here in our solver. So every time we call solve, we have a new memoization structure. How should we call this? Memo? Let's call it memo. let's make a new dictionary. And this is our lookup table. And it maps like joltages to the number of paths. Joltages to a number of paths. Actually, the joltage itself doesn't have to be long. No, the joltage itself doesn't have to be a long. This has to be a long. So the return value for calculate number of paths has to be a long, but the joltages themselves don't have to be. I'm not going to change it. It's not necessary, but I'm not going to change it either. So this is like a dictionary mapping joltage levels to the number of paths you can take to get to our device. Why is this flipping out? Because we need to call the constructor. There we go. So this is just a C# dictionary. You can look up stuff. You can add new entries. And that's why I was like a bit allergic to using this, because this is a mutable dictionary. You can do like memo.add whatever, a key and a value. And the thing I didn't like about it is it's this add thing returns unit, which is void. So this basically modifies the structure. It doesn't generate a new dictionary. And yeah, you can like it, you can dislike it, but I don't like it. But let's use this first, because it's a hell of a lot easier to understand than using an immutable data structure, or at least for me it was. So this is our lookup table. Let's provide our recursive function. Let's provide our lookup table as an argument. I'm just going to keep calling it memo for lack of a better term. And let's thread it into the... So now we did nothing. We just created a dictionary or lookup table, and we threaded into the function calls. It gets interesting, however, if we do something with it. And doing something with it is basically before we start any calculation. So the first thing we do in this calculate number of paths is look up, or try to look up, the value into the memo, or the... Yeah, let's keep calling it memo. And if we already calculated this for this particular joltage, let's just look it up, return the value, and say, okay, thank you, we're done. And otherwise do the calculation as we have been. So let's try to get it out. And let's type it. Let's first, I'm gonna open up this namespace so we don't have to type the whole namespace. There we go. So now we can just use dictionary. Yep. And let's use this type as well. So memo is a dictionary mapping integer 64s to integer 64s. And if we try to get the current joltage out of that dictionary, if we find something, then we're done. Otherwise, we have to do work. Now, there we go. So now we added memoization, but we're forgetting one important part, which is this dictionary needs to get filled. So now we need to fill it. And filling it is actually everywhere, every code path where you return something. It's like a new calculation has completed, so that should get added to the memo. So for example, here we're saying that whatever, if we only have one adapter in here, we have only one path, so let's keep track of that result. So let's say, oh, by the way, memo, let's add for the current joltage, let's add 1L. And then we can just basically look it up, but yeah. So we are keeping track of this result. There's another part where we do return something, and that's this case. Like if we have more than one element, we calculate the candidates, we calculate recursively, and we sum. So this part is also a calculation. So let's call it result. And let's add that to the memo for the current voltage as well. And then just return the result. So I think now we added memoization, or almost added memoization. So let's try to run it for the example again. Wow, that actually worked. Are you crazy? Yeah, that worked. So let's try to solve our input now. See if data does something. No, it doesn't, because it has to be a list and my current input is a sequence. So let's convert our sequence to a list. There we go. And if we run it now, we get a very big number, which is actually the correct answer. So 9968, 9968. So theoretically speaking, we added memoization and we are done. I want to go a bit further because I do not like using mutable data structures in my F# code. Although it's not that trivial to convert it to a purely functional, purely immutable solution. But let's try it anyway, just for the fun of it. So what's different? What's different if we, instead of using a mutable dictionary, use a map? And what is a map? It's also a lookup table, but it's a functional, or it's an immutable lookup table. So in a map, you can like do a map.find to get a value out. You can do map.add to add a new value. And the interesting part is, if you look at map add, it returns something. It's not unit, it returns a new map. So actually, instead of updating memo, we're creating a new version of memo containing this new key as well. So this is an immutable data structure, and you can add things to it and it'll return a new map instead of updating the existing object. That sounds fun to try, so let's do it. Yeah, let's do it. So memo is not a dictionary anymore, but a map. And this is where it gets interesting, because it has a try get. Cool, I didn't know that. So everything can stay the same. Sure, no, I don't like try get value. I like map.tryFind more. It's the same thing, except instead of true and a value, it gives an option. So it's basically, if it returns some value, it's dv, and otherwise, in a non case. Cool. But you see, there's some problems because we are kind of updating the map and not doing anything with it. It's like, this is an immutable data structure, so calling add to it does nothing, because it returns like a new map. It doesn't like update the object memo with this new entry. So our current approach will not really work because, okay, we'll generate a new map containing the new voltage and 1, but we'll throw it away directly because we'll return 1L and this new object is thrown away. That's not what we want. So this is where my brain got really fried and I was stuck for hours figuring out, like, is there a way to do this? And actually, there is a way to do this. I didn't find a generic memoization way to do it, and probably there is. If you've done it in F#, please share me your code because I'm really interested. But the way it finally clicked for me was when thinking about the return type of this function. So instead of returning the number of paths, like an integer or a long, instead of returning that, I just returned the memo, like the collection of all the calculated intermediate results. And once I did that, things got better. So without going too deep into the why, let's just make the return type of this a map of key voltages to numbers of paths. And let's go this way. So now, instead of returning 1, because this is the same one that we were memoizing or like keeping track of in our notebook, let's just add this to a... is there an add? Yes, there is. Let's just add the 1 for the current joltage to the map, and let's return this updated map. So now this is correct. And this is where it got really confusing for me as well, because actually, if you do a sequence.map and provide a memo, like a scratchbook with all the intermediate results, yeah, like if there's 3 candidates for a given joltage, then you would map over an array or a list of 3 elements, but they all use the same instance of the memo. And I would like to have the second candidate use the memo we calculated in the first candidate, and the third one use the memo we calculated in the first and the second candidate. So I wanted to thread this memoization through subsequent calls. And with a sequence.map, that does not happen, because yeah, that does not happen. But if you need to thread something through, the function that comes to mind is actually folding. And fold takes a folder function and a state, and the folder function takes the state, an element in the list, and returns a new state. So if we think of this folding thing as a... if you think of state as like the memo, things fall into place nicely. So this means that this function takes a memo, and it should return a memo. And we should provide an initial state, which is the memo. That's a lot of memos in a single sentence. Basically what we did now is fold over all the candidates, and we use the memo as an initial state for our folder, and we thread that memo through our recursive call. And the return type of this is not the number of paths, but it's actually like a memo, so a lookup table. Now, we still need to add like the currently calculated result to that memo. So we need to calculate the current result, because now we only like updated the lookup table. Now we would like to use those values. So how we do that is by, again, mapping over the candidates and saying like, okay, cool, we just calculated the number of paths for all our candidates. So in the returning memo, all the intermediate results are in there, so also all the results for the candidates. So if we try to, or not even try to, we're pretty sure that it's in there. If we find the tabulated result for this candidate, that's cool. And if we sum this, we have the result for this level of joltage. And if we do next memo and we add current joltage with that sum, let's call this sum, then we update it to lookup table for the current level as well. Now, what does it not like here? Oh yeah, candidates is not a list of candidates. Let's do candidates is the candidates. I'm extracting a variable, I mean, called cands. There we go. And use those candidates to do the filling of our tabular of our memo, and then use that same list to look up the values. Yeah, that sounds perfect. And yeah, candidates is not only the list of adapters, it's a list of adapters and the remainder. We don't care about the remainder, we just care about the adapters. Let's just do this. What? It's not defined? Oh yeah. There we go. I think we're almost there. So now we do the memoization, we fold it through, so subsequent candidates of the node we're currently visiting all use the same map basically. They use them one after the other, and if a step before or a candidate before generated a part of the search tree, the next candidate can use that tabulated information. And we're almost there, except that this function now returns the memo instead of the result. So if we just do a map.find our find our last value, we're there, and the last value is actually, let's extract this. Let device adapter is this, and if we paste the device adapter to the end, and if we look up the number of paths, is it device adapter or 0? It's 0, sorry. So if we look up the number of paths from 0 in the tabular, in the memo, we should get the same result. So bang, there we go. Let's run it on the example first. That looks correct. Let's run it on our actual program. There we go. So if you compare this to the dictionary one, it's almost identical, except that instead of like updating the dictionary as a side effect and using like a single shared object, now we have like purely immutable maps. And the trick or like the little hack we did was, instead of mapping over the candidates, we're folding over the candidates. So subsequent recursive calls can use a memo a previous step used. And that's a bit of the trick. It's not a generic memoization algorithm or a strategy to like introduce memoization for sure. And I would be very interested if you have like the generic memoization algorithm in your head, or if you have an example. But yeah, that's what I spent like 2 hours today trying to figure out, like trying to solve it with an immutable data structure. I hope you had fun, and I'll see you next time. Bye.